Okay, I hope it's working now. Okay. Summation notation, also called sigma notation. So let's talk about this because I need it now to put it in the limit. Okay. So the summation notation is basically a sum. We are not using this letter. We are using this letter. So this is the sigma, the Greek S. Greek S. So the sigma notation is the Greek letter S because it's more convenient to present from I equals 1. I is the index. 1 is the lower, not to be understood as the limit as LIM. No, the lower limit means the number, the starting number. Starting has nothing to do with LIM. Starting number. To 5, let's say, which is the upper limit, to be understood as the ending number, not the LIM, ending number, of, let's say, I squared. So this is the generic term. This is the index. You can have, normally the indices are I, K, J, something like that, I, J, K. So the index starts at 1. The sum says plus. We end with 5. And this is, I just chose I squared. We can choose other things, and we will choose other things in a minute. So what does this mean? So from I, the sum from I equals 1 through 5 of I squared means this. When I is 1, 1 squared will be 1 squared. The sum says plus. When I is 2, I have 2 squared plus dot, dot, dot when I is 5. So plus 5 squared. This is a notation, but like any notation will come with properties. In a minute, I'll explain the properties of this notation. But now, so what does this mean again? When I is 1, 1 squared plus. When I is 2, 2 squared plus. I don't have to list all of them. I can jump to the last one. I need to have exactly 3 dots and exactly 1 plus and 1 plus. Now, for example, if I say, what if I have 1 cubed plus 2 cubed plus dot, dot, dot plus n cubed? How do I write a summation notation or a sigma notation for this? Let's say with this time we want to use j, from j equals to whatever of whatever. Let's give it a shot. Yes, till
n.
Till the n from what?
I cube.
Yes,
J cube.
yes, we just changed the notation to illustrate with j. It doesn't matter. You can always use I. You don't have to change to anything. That's it. So what does this mean? Again, it's the condensed notation of this sum. When I is 1, the sum says plus. When I is 2, 2 cubed. The sum says plus. I don't have to list more than 2. Plus, dot, 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 plus, and I jump to the last one. Here's another situation. Let's say I'm asked to find the sum from I equals 1 to 10 from 2i squared plus 3. How do I determine this? Okay, so when I plug in 1, I have 2 times 1 squared plus 3 plus. When I plug in 2, 2 Let's put them like this so we see them. Times 2 squared plus 3 plus 3 dots plus 2 times 10 squared plus 3. This is cumbersome, especially because I have 10. So now I'm going to share my screen and click on this and click on math. And let's find where the summation notation is. Here it is. Up, up, up. Press enter. Oh, wonderful. X starts at 1, goes to 10, in parentheses, 2, x squared plus 3. Don't torture me, give me the number. Awesome. 800. Got it. So again, in math, go up to summation notation and enter all the information, of course, with x, no I, no j or k. Good. So remember, why are we talking about this? Because I need to put the summation notation in here. So that's why I'm explaining that, and we'll come back to fill this in. Okay, so now we know how this works, and there are a few properties of the summation notation. Let's list those. The sum from I equals 1 to n, as an example, from AI, the generic term. It could be I squared, it could be 2i squared plus 3, it could be anything you want. Plus BI, another term that has I in it. Well, of course, you're going to say this is like the limit, this is like the derivative, same thing. I'm going to also put minus here. So then the answer must be the sum of AI from I equals 1 through n plus or minus the sum of BI from I equals 1 through n. What does this mean? Same idea we had. The limit of a function plus another function was the limit of the first plus the limit of the second. The same thing we had with the derivative. The derivative of the first plus the derivative of the second. If I have minus here, I have minus here. The same type of property. Don't say that this is a distributive law. It's not a distributive law. So the sum of two generic terms is the same with the sum of the first generic term plus the sum of the second generic term. It looks like it's the distributive law, but it's not. Okay, one more property. So the sum of a constant times AI from I equals 1 through n, the same thing we had with the limit, we put it outside. The same thing we had with the derivative, we put the constant outside, the same thing. Exactly the same. So these are the properties of sigma. The properties of sigma. The sum of two generic terms is the sum of each separate. The sum of the difference of the two generic terms is the difference of those two. And if a constant is in front of any generic term, the constant goes outside. So for example, here, if I want to use this property or these two properties, I will have the sum of this and 2 outside plus the sum of this. So let me write that as an example here. So I could write the sum from I equals 1 through n from 2i squared plus 3 as 2 the sum of I squared from I equals 1 through n plus 3 the sum of 1. And you can say, why do you need that? I'm getting at something very important. 4 special summations. 4. And these have to be, I can't say remembered because you can use notes, but these are extremely important. The sum of 1 from I equals 1 through n equals n. That's number 1. Number 2, the sum of I from I equals 1 through n is n plus 1 divided by 2. Here's number 3. The sum of I squared from I equals 1 through n. This is the most difficult to remember. n plus 1, 2n plus 1 divided by 6. n plus 1, this n, of course. n plus 1, 2n plus 1 over 6. And the last one, I promise this is the last one, from I to the third is the same with this, but squared. n plus 1 over 2 from I equals 1 through n. These have to be remembered, memorized, whatever you want, but these are super important. If we want to prove any of these, we have to use mathematical induction. To prove, use mathematical induction. There is a method called mathematical induction to prove any of these. So the sum of 1 is n. The sum of I, n plus 1 over 2. The sum of I squared is the most complex, if you want. n plus 1, 2n plus 1 over 6. These two are very close. n plus 1 over 2, this is the same n plus 1 over 2, but squared. Okay. Any questions on this? Any questions on this? Okay. So now, finally, with all this information, I can go back here. So now I'm going to talk about the limit as n approaches infinity. Remember, n is the number of subintervals. 4, 8, 16, 32, blah, 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 approaching infinity, of the sum of areas of rectangles under the graph. Okay, and this is the exact area. So now, which page am I on? I'm on 11. So, area, I mean exact area, equals the limit as n approaches infinity from the sum from I equals 1, the first subinterval till the last one, of areas of rectangles. So let's stop, go back. Delta x, which is the base of any a rectangle of in any subinterval, times, which is constant, does not depend on I. It's always the same. That's why I put it in front here. Times, if I'm here, it's the first x1. If I'm here, it's on x2. If I'm here, it's on x3, and so on and so forth, of course, under the graph. So this is f, the function value, f of 0, f of 1, and so on and so forth, at that particular point, xi, because this one depends on where the interval is. If I'm here, it will be x1 for the first subinterval. If I'm here, it will be x2 for the second subinterval. So this index is the same with this index here. This is a constant. All this has a specific name. It bears the name of the mathematician who came up with it. It's the limit of the Riemann sum. Question: are we going to do this with a lot of situations? No. No. No, we cannot. We can do it with, and we're going to practice a lot, we can do it with linear functions, quadratic functions, and cubic functions. I don't have a sum for sine, or tangent, or arctangent, or the square root of I. I don't. So we can only illustrate the limit of the Riemann sum only with linear functions, quadratic, and cubic. So let's choose and illustrate. Let's choose a function. Let's choose an interval. So we can determine delta x. A function which can be, again, linear, quadratic, cubic. So degree 1, degree 2, or degree 3. There is nothing else we can illustrate with. We have to choose a function like this. We have to choose an interval, and we will be able to determine the exact area. I would like, if you allow me to, choose my favorite, because we already found 3 less than 4.5. Oops, it was 7, less than 7. We already found this. So all of them were approximations. So I would like us to use this function, and then I'll let you choose any function you want. This is our function. This is our interval. And to find the exact area. Is that okay with everyone?